Hello, everyone, and thank you for joining us today. This is our last Aviva Process Simulation training session. And I would like to inform you that next week I will send an email to everyone with the link and instructions for accessing those recorded sessions. So if for some reason you didn't receive the link, you didn't receive an email, just let me know. I will put my email in the chat in a few minutes. So just send me an email and I can forward this to you. And before starting, again, if you have any questions, please feel free to type them in the chat, and we will address all of them at the end of the presentations. Okay, Richard, I pass the floor for you.
Okay, thank you, Bruna. Let me share my screen. All right, so today's the last session, session 5, and we're going to be covering some topics that are optional this year in regards to the academic competition. So we don't suspect that you're going to need to use these features in this year's academic competition. However, they are very common and rather major aspects of the software, and we wanted to make sure that we presented them in some capacity, mainly for potential future competitions where these topics might be utilized. So we're going to start off talking about reactors and reactions, and then we're going to talk a little bit about columns, and then we're going to finish today about model writing, which is the ability to create your own custom models. Right, so let's start with reactions and reactors. When it comes to Aviva process simulation, reactors and reactions are two separate things. Right? You define your reactions in what's called reaction submodels. So you'll have an actual model in your model library where all of the equations and variables and so forth that are needed to perform the reaction calculations are written. And then you have reactor models themselves that you'll place on the canvas. And then within those reactor models, you will tell it, use this reaction submodel for a specific reaction. All right, so you define your reactions in submodels. You then use those submodels in the reactor models that are placed on the canvas. So that's the general infrastructure for how this works. Most of what we're going to be talking about here is going to focus on the creation of the reaction submodel. All right, that's usually the part that is the most troublesome. The reactors themselves are actually fairly straightforward models. There are 5 reactors that come with Aviva process simulation in the process model library. There's a conversion reactor, an equilibrium reactor, continuous stir tank reactor, plug flow reactor, and a Gibbs reactor. And we covered the Gibbs reactor 2 days ago in session 3. And that's the one reactor out of all of these that does not require any sort of reaction submodel or any reaction information. It works predominantly off of the Gibbs free energy for each component. All right, so that's the one where you don't actually have to do a lot of the things we're going to be talking about today. But for all these other reactor models, you're going to need to do some of the things that we do today in order for them to work. All right, now each one of these models is pretty straightforward in terms of what it's used for. A conversion reactor is for stoichiometric-based reactions where you're doing a conversion to one of the product components, right? Or you're converting a certain amount of one of the reactants, right? And it's a one-way reaction, so it's just until all of the reactants are consumed and whatever products you produce off of that, and that's the end of the reaction. It's not two-way. And with the conversion reactor, we can do multiple reactions. So you could have conversion reactions in parallel or in sequence, ones that work off of what was previously calculated or that run side by side. And when you see how we go about using this reaction generation tool that we have, there are different ways that you can set this up, and it creates a slightly different reaction submodel for use depending on the way that you want your reactions to behave. All right, so you'll see that when we utilize that. The equilibrium reactor is similar to the conversion reactor, but this not only requires the stoichiometry information, but it also requires equilibrium data. All right, so now you're going to have equilibrium reaction information that you're going to enter into your reaction, and this reactor is going to utilize that. And this is going to do your reaction and two-way sort of process, right? So it's not just going to be the reactants being consumed to produce products, but those products could, depending on the conditions within the reaction and the equilibrium considerations, it could also go the other way, right? And so this is a two-way sort of doing reactions when you look at it, the way that the reactions behave. And then the final two here, the CSTR and the plug flow reactor, those are what we would refer to as kinetic models. So your reaction submodel is going to have your stoichiometry relationships still, but it's also going to have kinetic data. And so you're going to have additional information you supply in the form of kinetic data for these two reactors to work properly. And the main difference between the two reactors here is really just about the geometry and how they tend to operate. A continuous stirred tank reactor is just that. It's a tank. It's constantly stirred, all right, to kind of maintain uniformity within the reactor. So there's a volume, there's geometry associated with the tank. There's a lot of physical related aspects to this other than just, here's my reaction and this is the conversion I want, right? That's the conversion reactor and the equilibrium reactor are less focused on the geometry of the reactors and more focused on just the reaction itself, whereas the CSTR and the plug flow reactor are going to have more of the physical or geometrical concerns that affect the reaction behavior. Plug flow reactor is more of a tubular reactor, has tubes that are coiled that run through the length of the reactor, and that's where the reaction occurs. So that's really the main difference between those. When you look at these models on the canvas, like if you took any one of them and placed them on the canvas and looked at their property inspector, what you're going to find are typically information related to how it's set up, like what reaction submodel you're using. If you have a rigorous submodel for pressure drop calculations, those types of configuration options, you're going to see physical information such as volumes or lengths, diameters, number of tubes, stuff like that. So physical related, geometrical related information. And then you're going to see operating conditions such as what temperature, what pressure, duties, your conversions, so those are going to be reported as well. And that's typically what you'll find in these, right? So when you think about that from a data entry perspective, the selection of the reaction is about all you do in terms of the uniqueness to the actual reaction itself, right? Because you're just selecting the submodel. Everything else is just sort of how the reactor operates. Whereas the reaction submodel, the part that you just made as a selection, is what houses all of the equations for how the reactions occur, right? And so everything we're going to talk about moving forward is all going to be focused on that reaction submodel, how you create those, what kind of information you're going to find in them. Now, all of these reactors, except for the Gibbs, are going to start with a default reaction submodel. This is to help ensure that when you place the reactor on the canvas, that it is square and solved. This is the same mentality that we have with every other model, right? We always want to make sure that when we place a model on the canvas from the model library, that the program remains square and solved at its default conditions. And so we have defaults here. There's two different default reaction submodels. Actually, I think there's more than two now. This is a little outdated, but there's default reaction submodels that each of these are using, right? And all these default reaction submodels are doing is setting the reaction rate equal to 0, which effectively means no reaction is occurring, right? So everything that comes in just comes out. So the default state of these reactors when you place them on the canvas and connect them is that whatever you're feeding to them is just going to come right back out. Nothing is actually happening within the reactor, and that's what gives it the square and solved state. So from there, what you're going to want to do is typically implement the fluid you're going to use, make sure it's nicely solving, everything looks fine, and then you add in the reaction submodel and you see if it converges from that point, right? So it's all about this incremental approach to building, which we talked about on the first day. The same approach is handled here with reactors as well. We want to make sure our feed is adequate, make sure we're using the right fluid, put down the reactor in the default state where there's no reaction occurring, make sure we're square and solve, and then we implement the reaction submodel and try to see if it solves using the reaction submodel. Okay, so how do we create the reaction submodel? In the past, before we had this tool that we're about to talk about, you'd have to do this manually. And while you can still do this manually, I highly advise not doing that, only because every reaction submodel has to be written in a way specific for the reactor you plan on using it for. And that's because there are certain parameters and variables that each reactor is looking for, even if you're not using them in your equations. And then if you're writing your equations manually, it's very easy to make a mistake where you enter the wrong sign, you misspell a component name, whatever the case may be, and that can lead to problems where the reaction submodel doesn't work properly. All right, so the reaction submodel needs to be written exactly as needed in a way that supports the reactor type you're using. And if you use this tool, which we're going to talk about here, that's going to ensure that it's set up properly for the reactor type you're going to use. All right, so we're going to open software. We're going to show creating a reaction using this tool, so that way you get a feel for that. And then we'll come and talk a little bit more about what you can do after the fact, after you've created a reaction submodel. So I have an example file open here. It's the CC8 example. This is the one of the files that's in the undocumented examples folder that I've been showing all week. This folder here has several other example files, as you see here. So conversion reactors, equilibrium reactor, CSTRs, plug flow reactors, right? Several other example files here that you can reference for different types of reactors. So if you're trying to figure out how to use a plug flow reactor, you may want to open one of these 3 files here and see how they go about setting up a plug flow reactor and how they write the reaction submodel and so forth. Okay? So we're using the CC8 example, and this file is doing combustion of isopentane in a conversion reactor. Right? So here's the reaction equation. And we're going to use the tool to recreate this. And then we're going to show how, once we create the reaction submodel, how we use it in a new reactor. So let's go to the Advanced tab. The first button here is the reaction generation tool. You click on it. It is an Excel-based tool. An Excel-based tool. When you first open it, right, it's going to look like this. The form is blank right now, and you're going to use this form to help you fill in the information required for your reaction. So when you do this, you generally start from the top down and fill out the different fields before you get to the point where you're actually picking and entering the stoichiometry for your components. So the first 2 areas here are for providing names of the model library and the model name, because it's the reaction submodel that's generated, that is going to be created from this tool. So in the end, when we're done with this tool, it's going to create a libx file, a library file, that I can come back to APS, import that libx file, and access my reaction submodel from there. All right, so at this point right here, it's asking you to give the model library, the libx, and the model in the libx a name, but you can always overwrite this at any point in time, right? So if you don't do it now, you can rename it after the library is generated, after you've imported it into your APS install, after you've copied over the reaction submodel to your simulation model library. There's multiple chances where you can rename your library and your model name. All right, so we're going to leave these as is right now, and then we're going to move on to the next part. The next part here is to put in how many reactions we plan on having in this single reaction submodel. When you put a reactor on the canvas and you go to choose the reaction submodel it's going to use, you only have a choice of one submodel, right? So if that reactor is supposed to support multiple reactions in it, you need to define all of those reactions within the single reaction submodel that is being selected, right? So if I have multiple reactions that I'm going to try to simulate, I need to increase this number to however many reactions I have, right? So if I make this 2, that's going to give me another form here where I can enter in reaction information for my second reaction. All right, so you want to make sure you set this first so that your form is set up properly to support the number of reactions you plan on having. I'm going to change this back to 1. The next part is picking the type of reaction you're going to have. And this type selection often goes hand in hand with the type of reactor you plan on using. So if you have a conversion reactor, you're going to pick one of these first 2 options: conversion parallel, conversion sequential. If you have an equilibrium reactor, you're going to want to pick equilibrium. And if you have a CSTR or a plug flow reactor, you're going to want to pick kinetic, right? Because each one of those reactors supports a different type of reaction, right? You'll see if I pick equilibrium, you'll see here equilibrium data, or if I pick kinetic, the form gets modified to include additional property information for those types of pieces of information, right? So either equilibrium data or kinetic data. And so this is going to expose the form and make it so that you can enter this information here. For this example, we're going to stick to the conversion reactor. All right, the next thing we're going to want to do is click this button here that says load components from fluid. The reason why we're doing this is that when you're using this form, you can actually pick from a list of components for your simulation file. But in order to do that, the form, the Excel file, needs to know what the components are. Right now, if I come over to this component database tab, there's no components to find. It doesn't know what the components are that are being utilized. So this button here is going to populate that information. So we click it, it opens up a browser where we can browse and select a SimX file. This can be any SimX file located anywhere. If you're trying to access your simulation files from your repository, you are going to have to navigate to the repository, which I talked about the other day. The easiest way to do that is go to this Sim Central Examples folder and go back 2 folders, then go to the Sims folder. And this will be your simulation repository. So I have the file here, CC8, and I can select it and I can open it, but I could have exported to a SimX file anywhere on my machine and then browsed in the spreadsheet to that SimX file and use that. Right? So there's different ways that you can access your files depending on whichever way you prefer. I'm going to select it this way. I click open. It now gives me a list of all the fluids that are defined in that simulation file. So these are the fluids in the simulations model library, this tab here, right? The simulation specific model library. So I can see there's my CC8 fluid, and I click OK, and it says it was successful in reading the components. I click OK. Now when I come over here, I can see it's populated with all the components. And when I come back to the form, now I can select those components in the form. Right, so at this point here, we're ready to start filling out our form to start, trying to create the reaction submodel. So I'm going to pick the components that are involved in my reaction: isopentane, oxygen, CO2, and water. Those are the components. And now I need to enter the stoichiometry values. And so we can come back to the file, reference them real quick. They're going to be 1, 8, 5, and 6. Okay, so anything that's a reactant is going to have a negative, so -1, -8. Now notice when I enter the value here for the product, populates this formula up here. Right? This formula is just showing you what you've entered so far. It's a way for you to just check and validate the formula and make sure that everything is working properly, right? This is not performing a balance, right? So let me try to make sure this is very clear. The form itself, this Excel spreadsheet, is not performing a balance on the reaction, right? So if you enter these values incorrectly, it's not going to care. Right? It's not going to catch that. Where it will catch it is when you go to use your reaction submodel in a Viva process simulation. When you come back here and you try to use your reaction submodel on a reactor, the reactor is going to either fail to solve, or it's going to solve but flag a message telling you that the reactions is basically in balance, right? There's not a balance going on between the number of moles of things that reacted away and number of things that were produced, right? So that's where the check and balance is going to occur. But at this point here with the form, this little equation that you see here, it's not checking and balancing your equation. It's just simply reporting what you have typed here. Right? It's for you to be able to reference and check. All right, so that's all that this is showing. Once I've filled out my form and I'm satisfied with what I have here, I can click the Generate the Viva Process Simulation libx file. I can browse to where I want to save the file. Now, remember, this is a libx file, right? So when I save this, it tells me where I saved it to, that it was successful. I'll click OK. I now need to come back into here in the Viva Process Simulation. And to import a library, I need to be in model writing, right? So I need to come over here. I need to go import library. I need to browse for my libx file. I need to click open. Now, I already have one that has that name from me demoing this in the past. So when I do this, it says the imported library will be renamed to the next available name. So I say import. So I get the name lib1 instead of the name that it says it is. And that's fine. That's not a big deal. I could have also shown the one that I had before and deleted it prior to importing the new one. And that would have then, when I imported it, would have retained the default name that I had. All right, so now I have the library imported. I have my generated reaction submodel. I can open it, I can look at it, see how it wrote out the reaction information. Right, and now I want to copy this over to my simulation model library. Now, I copy it over to my simulation model library because I want to use this in my simulation, right? And so it's going to, when I put this on the reactor, it's going to be pointing to the model library where I'm using the reaction model from, just like I do with fluids, right? And so if I don't copy this over and I simply point it to this lib1 model library, when I create my simx file and I give it to someone else, or I try to use it again in the future, and I import it, if I don't have lib1, it's not going to be able to find the reaction submodel, right? So it's always good practice to store your customizations in your simulation model library. And so I have it stored here now. And now what I'm going to do is I'm going to add a source. I'm going to add a conversion reactor. And first thing first, I'm going to check, make sure I'm square and soft, right? I'm going to keep an eye on this as I do this process. Now, right now, there's no reaction occurring. So when I come in here, there's nothing happening. If I look at my reaction results, there's no conversion whatsoever. Furthermore, I'm still using the default fluid. So my components aren't even up to date yet, right? So I want to use the proper fluid. So I switch this over. Now I can see I have my components updated here, but again, still no reaction occurring. And now I want to change this RxN model type. That's your reaction submodel selection. So this is the default, and I want to change this to use my generated reaction submodel. So I change it to this. Now I'm using my reaction submodel, right? But again, notice no reaction occurring. So even at this point in my process, the simulation's designed not to be doing any conversion up until this point. The program, it tries to take as much incremental steps as it can to ensure that you remain square and solid, right? And so the transition from the default submodel to this submodel, we want to be seamless so that now from this point, we can start to try to introduce some kind of reaction. Now, for me to get a reaction, I do need to make sure that my composition here is adequate, right? So right now I only have pentane. I don't have anything else. So let's add 8 kilomoles of oxygen. Now I should have sufficient reactants in order to do a reaction. Right, so now we're going to change this over, and we can go straight to 1 for 100% conversion. We can go to some value in between. It's probably safe that we start off slow and just make sure that it solves. All right, so we do 10% conversion. All right, that worked out just fine. Let's try maybe 50%. Oh, no problem. It failed to solve. Now, if you get an issue like this, where it fails to solve and it says something like a value is at an upper bound, it could be, and it is in this case, the fact that your fluid has a default max temperature or pressure that is lower than the feasible solution value, right? So when you go into a fluid, here's the fluid editor, there's an area for starting values. And in here, there are minimum and maximum limits for pressures and temperatures. And so this value of 2000 Kelvin, it's telling me right now that it can't solve because this is on its upper bound, right? So I could increase this. Maybe I make it 5000. All right, and that just makes it so that it can go above that 2000 point. So now just changing that limit, it's solved, no problem, right? And we can see the temperature is actually around 3100 Kelvin, right? So significantly higher than that 2000 limit was. And I can keep going with this. I needed to go higher. And again, this might not be feasible. I might have some other constraints within the way that my simulation is defined because of all the default values that I'm just assuming are being used here, right? So I probably need to change my operating pressure so it's not such a high temperature. Probably need to change some other conditions, but you can see how we go about utilizing this, and we stepped ourselves up to a 100% conversion in this case. All right. So this is the general overview of how to use these, how to set up a reaction submodel and then use them. One more thing I want to cover before we move on is understanding the structure of the reaction submodel. And the reason why I want to cover this is there may be times where you need to tweak the information here. You need to create the reaction submodel at a base level and then add in some modifications to it more manually, right? And so what you can do is once you have this reaction submodel, you're able to adjust this any way you see fit, right? So I can write my own equations at this point. I can put in my own variables for those equations at this point. I can do anything I would normally do modifying any model, all right? But in order for me to do it properly, I need to understand what is currently here so that I can work sort of within the framework of what the reactor and this reaction submodel is looking for and utilizing, right? So when I look at this, this is for a conversion reactor. What I'm seeing here is that there's an overall reaction rate equation written. That's this DZ-RxN1 equation. This is for my overall reaction rate, and it's based around the base component of isopentane. All right. When I look at the individual rates of each component, that's what these equations are here, they all relate back to this overall rate, right? So the way that we write our equations typically, we relate the individual components to the overall reaction equation, and we input the stoichiometry there, right? So every time this reaction occurs, it's -1, isopentane, -8, oxygen, +5, CO2, +6, water, right? That's how much we're utilizing based off of the main base reaction here, right? If we had multiple reactions here, we would see another overall reaction rate for the second equation and the third and the fourth and so on. And then every one of these individual component rates would relate back to every one of the base rates, right? So if I had another combustion reaction, let's say I was combusting butane instead of isopentane. Well, the combustion of butane also uses oxygen, CO2, and water, just with different stoichiometry values. So you would see modifications to these oxygen, CO2, and H2O equations where it does this and then say plus, the stoichiometry value of the next equation times its base equation, right? Something like that. That's how you would see this written, right? So we have the ability, as you can see here, I'm not going to commit this, but we have the ability to tweak these, and understanding sort of the way that they're currently written, how they operate, is going to allow you to tweak them better. All right. So that's the base way of writing the rate equations. We also need to account for the components that are not included in the reaction, right? All the components we would consider inert, right? So any component that is not participating in the reaction that's going through the reactor still needs to tell the reactor what to do with those components. So you're always going to find this type of equation here where it says the rate of the components that are not the components in the reaction, right? It's always written not the components in the reaction. That's how it's written, because we don't know what these components are going to be. Could be any number of other components other than these. So we can't write something that specifically says this component, right? We can only say not the ones that we do have, and those are equal to 0. So this is how we write our rate equations for components that are not participating in the reaction. All right, one last thing that I'm going to point out here, and then we're going to look at some things in the slides about reaction submodels. The thing about these equations that's important to understand is that when you write a component name, it has to be the name exactly as it's written in the fluid. So I have this fluid here. Wait for it to pop up. And the components are named under this column: isopentane, O2, CO2, H2O, N2. Those are the names of the components. Let's take H2O, for example. H2O is water, and we commonly refer to it as water as opposed to H2O, but people use it interchangeably. Your reaction submodel is only going to recognize this as H2O, because that's the way it's named here. If you were to instead do something like this and call it water, it's going to fail because it doesn't know what that component is, right? It doesn't know what water is, right? It knows that component by the name H2O, not by the name water. So you need to make sure you're using the exact naming of the components as they appear in the fluid. So back to the slides real quick. I want to show you an example of equilibrium and kinetic equations. So here's an example of, and I'll make this full screen real quick. Here's an example of equilibrium equations. Notice they still have the individual rate equations for the components in the reaction, but they are also including the equilibrium equations. Now, here Yeah, this one, we don't see a direct relationship between the two, right? You don't see anything up here in the equilibrium reactions that relate back to any of these rate variables or this R1 variable or anything like that. So the common question when you see this is, how is it actually implementing the equilibrium data? And you're going to have the same question with the kinetic data when you see that on the next slide, right? The way it's done is within the reactor. The reactor itself has the relationships between these different variables. That's why we use the tool to generate these reaction submodels, because the tool knows what each of these different variables is called within the reactor. And it's going to make it set up in a way so that those relationships are able to be utilized within the reactor, right? So when you see your reaction submodel, you see, equilibrium or kinetic data, and then you see rate information, which is all stoichiometry based. Don't be concerned that it's not utilizing your rate or kinetic data properly, because it's not in here where that's happening. It's happening in the reactor itself, where those relationships implement the kinetic and the equilibrium information. Here's the example of the kinetic data. So you can see kinetic equations up here, and down here we can see our rate equations. Now, ironically, with this specific example that I'm showing on the slide, we do see the relationship here, R1 being used in the rate equations, and then R1 relating to RR and RF, which are part of the kinetic data. So we do see a relationship here, but this is an older screenshot of the way that we used to sort of write these reaction submodels. You might not always see it so cut and dry in the way that the reaction tool generates the reaction submodels. Okay, so with that, that's pretty much everything I was going to cover with column or with reactions and reactors. We're going to move on to columns now. Now, let's see. Let's start with just this slide as I talk about columns in general. So a column model in the Viva process simulation is representative of any type of distillation kind of column that you might have, right? It just depends on how you go about configuring it. So it could be an atmosphere crude column, could be a vacuum column, could be an absorber, a stripper. It really doesn't matter what the column is. It's going to be based on how you connect streams to it, what kind of configuration options you include into the column. The way that you go about setting it up, that's what's going to dictate how that column behaves, like what type of other column it behaves as, right? So we have one and only one column model. Mainly, I will clarify, there's a specifically an extractor column model that is available to you here, which is a simplified version of the column for extraction purposes only, right? But the main column model is the one that you're going to use for pretty much any type of column that you're going to run into. All right. One of the things about the column that I always like to point out is that the help documentation is very extensive for the column model. Columns are very complex models. They have a lot of equations and complexity to them. And the more that you include, the more that you configure, they tend to get more and more complex. So when you're trying to learn how to use the column and how different features work within the column, it's a good idea to review the help. Now, when you go to this help, you're going to find it's so long. You can see me scrolling, and here's a little scroll bar here. It's so long, it has its own table of contents here to help you find things easier, right? So there's quite a bit of information here, and it's a good resource to learn more about the column and how it works. But you do have to dig through this documentation to be able to find certain pieces of information. I will say at a certain point, right around here, it walks you through an actual step-by-step building a column from scratch all the way through to a dynamics simulation. That process that it walks through is what I'm about to demo to you here. Right, so you're going to get to see it here. But if you need a refresher, you can always refer to the help, and that can tell you about some of the different steps I'm about to do. Now, when it comes to modeling the column, there's a pretty general workflow that you should follow for all columns. All right, so the first thing that you're going to want to do is just make sure your simulation is ready for your column. All right, being a column, it's designed for separating specific components where every aspect of the column is fine-tuned towards the specific components that are coming in. You want to make sure your simulation's square, solved, and your feed is accurate, right? You don't want to be messing around with your feed information after you start trying to simulate the column, because that could give you some difficulties getting it set up initially, right? So this is not to say that you can't change your feed to the column at a later point. That is definitely something you can do within the software. But generally speaking, you'll find it's a lot easier to get the column built and solving and working properly if you start from the proper state to begin with. All right, so want to make sure you're square and solved and that your feed information is ready to go. And then when it comes to building and using the column, we generally follow these 5 steps that you see here. First thing first, put the column on, connect it to the feed, and just make sure that's solving. Make sure there's no problems at that stage, right? Get familiar with the way that things are looking already in the initialized state of the column. And then we're going to work towards getting an initial conceptual design as the next step. All right, so when we say an initial conceptual design, what we mean is one that is solved using rigorous thermodynamics and is achieving certain base level requirements that you need for your column. This could be, just achieving the overhead product specification, right? Whatever the composition is that you need overhead, right? That might be the goal, right? And so we're generally going to do certain steps to achieve that, and it's going to be very minimal in terms of what is required in order to achieve that level of design. And then from there, once you have that initial design, you might want to get more in depth with the column. So you might want to start to simulate more detailed design of, say, your condenser or reboiler. If you want to externalize them, you might want to start to size the column. You might want to balance your pressures, adding controls to get you ready for fluid flow and dynamics. So there's a bunch of little things that we can do from that point, but a lot of these tend to be more involved or not 100% necessary in most typical conceptual designs. All right, so we separate these 2 steps out to kind of distinguish one from the other. By the time you get through step 3 here, you're pretty much done with everything that involves you working with adding to tweaking the column. And now it's just a matter of using it, right? And so you switch to fluid flow, you do some flow distribution analysis, you try to change some set pressures on controllers or pressures around the column and see how that affects the flow distribution through the column. And then you switch it to dynamics, and now you're actually performing transient studies where you disturb the steady state, you make a change, then you see how the column responds to that change. So this is the general overall workflow that we recommend. We're going to be focusing a lot on these first 2 steps. These first 2 steps are very important because you're trying to get an initial solution. And the way that we do that in the software tends to be more manually than what we have in other software. And so you're going to see me talk about this quite a bit and walk you through this. Now, everything in this process, and I have a lot of slides here that we will not be utilizing, a lot of this is going to be demoed, right? But the first part that we're going to be focusing on is this goal here of achieving an initial rigorous solution. This is not your conceptual design solution. This is just a rigorous solution. And it has 6 steps. We're going to add, we're going to tell it how many number of stages we have, what the feed tray location is. If we have a condenser or reboiler, then we're going to set it to what's called solve mode. And then we're going to set contact equal to 1. And I will say 95, 99% of the time, this gets an initial rigorous solution for any column that we have. All right, there's occasionally times where this doesn't work, and there are usually very specific cases, but most columns, this is going to work all the time to get you that initial rigorous solution. Give me 1 second. I've been fighting a cold all week, and this is surprisingly the first time I've had to blow my nose on camera, so my apologies for that. All right, we're going to switch over to the software, and we're going to demo building out a column from scratch. And as I do this, I'm going to talk to you about the concerns related to the workflow process and the typical things you're going to want to do on working with a column. So again, first thing, make sure I'm square and solved. Make sure my feed is ready to go. So in this file, we have a methanol water column that we're going to be trying to separate. This is not a very complex simulation. This is going to be pretty straightforward. All right, so this is just two components, and we're just going to separate them out. First step is going to be adding the column onto the canvas. When you add the column initially, you're probably going to want to resize it because it comes very small to start. And then we're going to want to connect the feed to the column. Now, the very first thing you're going to see here before we do anything else is that the column is, or the simulation is square and solved. And you may be asking yourself, how? How is it square and solved? We didn't do anything, right? All we did was connect the feed, all right? We have yet to even touch the column and do anything related with the column. The reason why it's able to say that it's square and solved is that at this point in the software and in working with this column, the column's in a mode called configure mode, where we are trying to initialize it and get it to a rigorous solution. The solution that it's achieving right now is one that we call a no contact solution. It's an assumption-based solution where there's no actual separation occurring. Everything that's going into the column, the vapor goes up and the liquid goes down. And it's as simple as that. All right. This is a way of starting the column to help ensure that we're square and solved and that we can sort of build upon this to get to a rigorous solution. One of the things that we're going to be doing while we're in configure mode is trying to get a certain set of properties populated as initial estimates. So we're going to refer to this area for profiles, and there's this vapor and liquid from tray to tray, right, that we can see here in the profile section. Right, so when the feed comes in, first off, it defaults to feed tray 1. All the vapor just goes up and all the liquid just goes down. And that's effectively what you're seeing right here. All right. Our goal is going to be to populate some kind of values on all of these trays here. Right. And that's going to help the column solve more robustly when we switch it from configure over to solve, where we use the more rigorous thermodynamic based separation calculations, right? So right now, no separation is occurring. It's using very simplistic equations to solve all of the column mesh equations, right? All the different equations that it's trying to solve for all the various properties, right? So we're trying to populate some initial values so that when we try to do the more rigorous calculations, it has these starting points to start from. It's more likely to solve. Right? And the way that we do that, the way that we populate this is those 6 steps that I just talked about here. Right? So we're going to change the number of stages. We're going to make it 13. We're going to change the feed tray location. This is going to come in at 7. So you can see this is adjusting, right? We have more trays. The feed's coming in the middle now. Vapor's still going up, liquid's still going down. Next part is we're going to choose if we have an internal condenser or a reboiler, right? So we always want to start with an internal condenser and reboiler for a couple different reasons. One, if we do an internal condenser or reboiler, it's going to be attached to the column and solve as part of the column, right? So that we're going to see all the information related to the condenser and the reboiler within this column data entry window, and that's going to help us to get a solution that's uniform and keeping everything sort of together within this one model. Right. On top of that, if we get this internal solution first, when we then later externalize and switch this to external, we're going to have certain pieces of information that are saved from our internal solution as sort of placeholder values that help us when we externalize. It's going to help us to retain the solution that we were at. So that when we are externalizing, all right, and the process of externalizing means we are using other models from the model library outside of the column to build out a condenser or a reboiler configuration. While we're doing that, we're still guiding the solution to stay at the same values it was at from the internal solution. So it's to our advantage to keep this internal solution and start with that, right? So when we pick whether or not we have a condenser or reboiler, if we have an internal one and we add it, what we're going to see is that a condenser gets added to the column, right? The icon changes. And we now have variables within the column's data entry window that are related to the column. Pcond, dpcond, reflux ratio, vapor fraction, condenser. We even have a whole section devoted to condenser properties, right? One of the things that you'll notice about this that might be different from other software is that the tray numbering, right, so number of stages up here, does not affect the column's condenser or reboiler. It's simply the main fractionation portion of the column, right? Just the trade section, right? So adding a condenser does not change my number of trays, right? Some other programs, if you add a condenser, you have to increase your number of trays by one because technically the condenser is going to take the top tray as for itself, right? And similar concerns with the reboiler. You don't have to worry about that here, right? When you add a condenser or reboiler, the number of trays stays the same, and they have their own properties that are shown within this window, right? Now, when I added that condenser, when I look at the profile, the first thing I'm going to see here is that I now have some values here where there are values of 0, right? So the condenser, when I added it, has these specifications that came along with it. Reflux ratio of 1 and a vapor fraction of 0, which assumes a total condenser. So everything that's going up is condensing and coming back down, right? But since the reflux ratio is 1, 50% of it goes as reflux back to the column, 50% goes out as your product, right? Your liquid product, right? So we have 9.9 kilimoles an hour coming up the column. And then we look at it, we have 4.9 kilimoles an hour coming down the column, which is basically 50%, right? If we do the same thing for the reboiler, we're going to see similar behavior. We add a reboiler, icon changes, new variables are added, new sections are added for the reboiler, right? And our profile, yet again, changes. So part of that flow that was coming down was like 900 and something, right? 50% of it's coming back up. Then when it gets back here, it's flowing up back towards the condenser and well, sorry, this is the up. This is the vapor going up, right? And 50% of that's going to come back down. Right? So we can see we're starting to fill out this profile with some values, right? And this, we're focusing on the vapor and the liquid, but this also happens with the temperature, happens with not the pressure, because we're going to set the pressure profile, happens with vapor fractions, happens with a lot of these different properties, right? So the goal here is that provide initial values for the column so that now when we take it and we switch to solve mode and we try to get a rigorous solution, a real solution, we are much more likely to see success when that happens. All right, so now I'm going to switch this over to solve. And now we're square and solved, and our column's no longer red because we're no longer in configure mode. So now what this is trying to tell you is that you have a real solution, right? One that's based on the actual thermodynamics here. However, let's look at that solution. This looks an awful lot like the solution from the configure mode. Right? So what's happening here? Simply switching from configure to solve is not enough, right? What happens when we switch the configure from configure to solve is that the program changes the set of equations that are being utilized to solve the column. And the solve equations are actually a combination of the equations we were using before in configure mode and the equations we are trying to utilize now in solve mode for the rigorous calculations, right? And so what happens is all of the equations that are being used now in solve mode, it's almost like a toggle. The old equations are being utilized times 1 minus the contact value, where the new equation, right, are being utilized times the contact value. And so as this contact value changes, we toggle from one to the other. Right now, with the default of a value of 0, we are using only the configure-based equations, right? Because it's those equations times 1 minus the contact. 1 minus 0 is 1, so therefore it's using those 100%. The solve equations are being multiplied directly against the contact. Since contact's 0, it cancels out that term in the equation. As we flip this and we go up to 1, we slowly eliminate the configure equation and start using the more rigorous equations. So in a way, this contact value works kind of like an efficiency, all right, which is why you have this efficiency parameter here and it's set to contact. All right, it's not a real efficiency. It works a little bit differently than, say, Murphy efficiency, which is more of a real efficiency calculation. All right, but it works similarly. So, but right now, with contact equal to 0, we are still doing the assumption-based equations. That's why our results haven't changed. If I change this to 1, now I see the rigorous solution, right? And this is an actual solution. It's a real solution, and you can see the results here, right? So just to recap these 6 steps that we talked about before. Set the number of trays, P tray location. Do you have an internal condenser and reboiler? Set this to solve, set contact equal to 1. Now you have a rigorous solution. In other software, everything that we just did there would have been handled by something like an initial estimate generator, right? So Pro2 is a good example of this. You have initial estimate generators in the column. They take the very little bit of information that you've provided to the column, and they come up with initial values for all of these properties that we have, like the vapor and the liquid tray-to-tray flow rates, right? And then it sends that information to the algorithm, like Inside Out or Sure or ChemDist within the Pro2 column. The algorithm then solves the column, right? Well, in here, you are the initial estimate generator, right? While this is in configure mode, you are the one that's doing the initial estimate generation. And then when you switch this to solve and contact equals 1, you're supplying the algorithm, in this case, APS solver, with the initial estimate values in order to try to solve the more rigorous calculations. Right? So this is how it works in APS, and this works, like I said, about 95% of the time. Occasionally, when this doesn't work, it's usually because of these base assumptions that came with the condenser and the reboiler, right? And so you can work with these. Let's say, for example, you had a fluid here that was all vapor, right? And a vapor fraction of 0 wasn't achievable. that would be a reason why it might have failed to solve when you were in configure mode. And you might have needed to change this to something like, 50%, right? Just to get a solution while in configure mode. And then you can swap it over to solve, and then it should work more robustly, right? But there are occasional issues like that you're going to run into with this process. Usually it's going to work most of the time. Okay, so this is just to bring it back to these steps that I was talking about before. We just did this, right? Now we're trying to get to this, right? We're trying to get our initial design. And so one of the things we can do is we can add some sinks. Maybe, there we go. And we can look at our product purities and see what is our current solution actually achieving. All right, so we're doing pretty good on separation of water, right? We're way above 99% water, right? But the water, or the methanol purity, is not very good, right? So we want to try to improve this. Now, in Aviva Process Simulation, adjusting for this value is as simple as swapping specs, right? In other software, you might have to go into the column and set up some kind of special specification, define a variable, get it all configured, and then when you run, hopefully it meets the condition that you're looking for. And here, check, check, change value. It's as simple as that. Right, so that's all I have to do in order for me to start meeting my desired conditions. All right, now there's other things I'm going to want to do. This is not exactly the final values that we're going to be going for. So one, I might go for a less pure value here, and I don't exactly have a reason for this other than this is what works best for this demo specifically. So we're going to set that value like that, but there might be a reason for you to have to spec this as well and swap out the boil up ratio in this case. We also want to set our pressure profile. We haven't done that yet. If we look at our pressure profile down here, you can see it's constant pressure, right? So we're going to come up here and we're going to add some pressure drop to every tray. All right, so now we can see we've adjusted our pressure profile by adding in a little bit of pressure drop per stage. Right, that's what the DP stage means. There are a couple different ways that we can define our pressure drop. We can do it constant like this, which means no matter which things that I've specified here in this window, all right, by swapping specs around, it's always going to retain a constant equal pressure drop from tray to tray. That's what this means. We can also do profile, which would allow us to have different pressure drops at different stages of the profile, right? So if I do this, it's a 2 kPa pressure drop all the way up until here, and now it's 2 plus the 5 that I entered, so 7 kPa pressure drop from these, and then I added another 5. So you can see it's not constant from tray to tray. And there's different ways that we can work with this to get different increments. This way right here with the DP step variable is actually a cumulative change that trickles down through the column. So it starts off with the 2 from here, and then it adds 5 here for the next couple stages and adds another 5 for the last ones. But we could also swap that out with hard-coded pressure drops from tray to tray. We can swap it out with the actual pressure profile itself to specify certain pressures on certain trays. And then there's this last option here, which allows you to use a rigorously calculated pressure profile from a submodel that you may have created. And we're going to talk more about this internal setting in the next part when we start talking about sizing the column, right? But if you wanted to use your sizing submodel for the rigorous pressure drop calculations, you can do so by switching this to internals. All right, we're going to stick to constant here, and we're going to stick to the 2 kPa, so everything looks good now. All right, and at this point, from a conceptual design basis, we could say we're pretty much done with this, right? We have a pressure profile entered. It's using our pressures. We've entered in our product purities here. Everything else looks reasonable. There's not really a whole lot that we have to do at this point with the design. So we could say at this point that we're done with this step, right? And we could move on to the next step. Now, the next step is when you start to do a lot of the additional things that aren't necessarily required, but may be useful for either getting a more detailed design of the column or for preparing you to switch to fluid flow and dynamics. All right, so the first thing we might want to do is size the column. You can come to here, stage sizing, and there's a parameter here called capacity. It's set to ignore by default. All right, now this capacity parameter, what it does is it toggles on the sizing calculations, right? If it's set to ignore, then there's no sizing happening right now. And when we look at this, we can see there's some default information for things like the diameter of the column, heights of each stage. These are default values that are just there to start off with, right? But it's not actually calculating any of these values or doing anything with them. Right? If we switch this to internals, you'll notice it adds a flooding factor calculation, right? And we start to utilize specific submodels for rigorously calculating the values that we see within this area. And so if we come down, this is the setting to turn it on. But if we come down here where it says stage internals, we can actually see what submodel is being used from tray to tray. And now there are 5 submodels that come with the software by default. There's the simple tray, trays, Sticklemeyer, Sulzer packing, and KG packing. The simple tray and the trays are for trade columns. The trays one being a little bit more rigorous when you want to start to get into more detailed tray design. The Sticklemeyer is for packing, random packing, and you do have options for what type of packing you're going to use. And then the Sulzer and KG are for specific industry packing methods from those companies. Right, so we have different choices that are available to you here, but you could theoretically create your own submodel to calculate column size, flooding factors, pressure profiles, and so forth. And then you would just use them in these selections here. We're going to stick to this simple tray setting. And for us to size this column, probably the easiest way to do it would be to swap out the column diameter, right? This is the thing we're trying to calculate, and then just set a flooding factor for the column. Now, the flooding factor that was being calculated for this column based on this size was 215%. Right, so that's not really a very reasonable value to use. So what we're going to want to do is we're going to set this value to something more reasonable, like 70%. And when we do that, it back calculates the diameter required for a 70% flooding within the column. Right, and so now we're sized. It's as simple as that. There's not a whole lot more that we have to do. There's more that we can do, but nothing that we have to do really at this point. Right, and so what we're going to do is we're actually going to swap this back. It's always nice to have the column diameter specified and have the flooding factor be calculated, but you could have left it if you wanted to. And we're going to move on to the next part. So now what I might want to do is externalize the condenser and the reboiler configuration. Right, so we're going to start with the condenser, and we're going to look at this area here before we switch it over. This area here has results right now that are related to these conditions that we're trying to meet within the column. Right, so these are the results that correlate to this composition for our product purities. And when we switch this to external, some of these values are going to stay, and they're going to stay as specifications to help ensure this solution state. Okay, so I'm going to switch it over to external. Now, first thing you're going to see when I did this is that I'm unsquare and unsolved. All right. Reason why that's the case is because this didn't automatically reconnect, as well as I still have specs outside of the column that weren't inside the column, and it got rid of the condenser, so there's technically no more reflux ratio variable, which is what we utilize to swap these around. So one of the things you might want to do before you do that switch over to external is swap external specs back in to the column so that your column itself is sort of internally square, right? It has all of its default conditions specified, all right? And for this issue here, if my product was a vapor product, it would have automatically reconnected. But because it's a liquid product, I'm going to have to reconnect it once I switch over. Or I could connect this to here and it would then reconnect when I switch it over. Right? So either way works. But now when I switch this over and I connect this, now we're back to being good. Right? And you can see here, it's calculating that value. It's no longer specified. It's calculating it based off of these reflux conditions that are being used inside the column to maintain this solution. All right, so now I want to start building out my column. And if I am smart and I have a template file like I do right here, I can simply copy, paste this over into my simulation and quickly copy over my condenser externalized configuration. All right, so I have it copied over. Here's the product stream. I'm going to disconnect it from here. And I'm going to connect it to my condenser configuration. I'm going to get rid of this because I no longer need it. This variable here was to that other sink, so I don't need that anymore. Okay, and then I'm going to connect the reflux. Now I'm back. I'm square and solved. I'm externalized. Everything's happy. And I check my results. Still at 96% methane. Right? So I'm still achieving the same solution that I had before during the process of externalizing. Now, I did a copy paste. If you don't have that as an option, you would have to build this out. And so what you would do is you drag and drop the heat exchanger. You'd disconnect from the sink and you'd connect the overhead to the heat exchanger. You'd add in the other side of the heat exchanger. You'd add in the product going to the drum, right? And you'd add in this drum model, and you'd literally go one model at a time until you build out this entire network and reconnect it back to the column. All right. So that's how you would do it if you're doing it manually. But one, because I'm doing a demo, and two, because it's kind of cool looking seeing the quick copy and paste. I have this parts file that I use. Now, I also want to point out, especially for the students on this call, this is not the way that every condenser is going to be built out. Just because you see me having it built out this way doesn't mean that this is how every condenser is built out. The whole reason why we externalize condensers and reboilers is because every condenser and reboiler is different and has different ways of being configured, right? So this is a pretty straightforward standard way of simulating a condenser build out, but this is not always going to be the same for every single column, right? So just want to make sure that that was clear. All right. We're going to do the same thing now with the reboiler. So we're going to come here. We're going to switch this to external. We can see it's saving that information. Oh, and by the way, here's the condenser. These are back to being calculated now. Now that this is back being connected again, these are back to being calculated. All right, so here's the old solution that it's saving. We are going to have a sump here because we're going to try to draw off of the sump to go to the reboiler. The product of the column, the bottom's product, is still going to be this stream coming off, but the reboiler itself is going to come off of a separate draw and then return back separately as its own loop within the column. right? So when we do this, we need to add a sump. Now, good practice with a sump, and there's a whole reason why these are here. Go to initialize first, right? This is just going to help make sure we get it started, and, implementing it. It helps ensure a more robust solution, more likely that you're going to get this to solve. Once you get it to initialize, then and if it's square and solved, then you can switch it over to single, and it should stay square and solved at this point. And I'm going to come over, I'm going to copy this, paste, and connect this together. Something happened with my demo. There was a little error that popped up and something got thrown off. So I'm not entirely sure what just happened. I'm going to delete these. We'll just, what we're going to do is try to manually build this out real quick. We'll copy these over. Seems to be failing with this for some reason. All right, apologies for the issue with the demo. Let me see if I can get this up and running real quick, and then we'll move on. Is that the right side? It's not the right side. This is not going to work out the way I want. All right. So for sake of time, we're just going to abandon this part of the demo. It's normally works, but for some reason I got some kind of error when I copied it over, and it's not working right now. So we're going to just assume that this worked out when it came to copying over that configuration and connecting it. And it should have been as simple as just connecting this over, and I would have been square and soft. But since it wasn't, we're going to move on, and we're going to show the next part. Ignore the fact that this is not solved. We're just going to press forward with the next part because there's only one more thing I wanted to show, and then we're going to be done with the column. All right, so the last thing I was going to show is that a lot of times with these columns, you want to balance your feed pressures coming in. Remember, the column is using a fixed pressure profile, right? So this pressure profile is defined here, right? And so it has these values coming in, but your feed conditions are not always going to be the same as what they are on the tray, right? So I have a feed pressure of 150 kPa. It's coming in on tray 7, that's 113. So it's not the same right now as what is in the column. So if you want to balance them, you want to change the inlet parameters to balanced. And then you are going to have to resquare the simulation by basically the number of feeds that are coming in. And so we can square this one here by unchecking this. We can square this one here by unchecking this. And for the feed, we really don't want to free up the pressure in the feed. So what we can do is we can add a valve first and then free up the pressure drop in the valve. And that can help us meet the requirement here. And now when we look at the feed pressure coming in, it's 113, just like it is on the feed tray. Okay. Now, if this had worked with the reboiler, I would have taken this to fluid flow and dynamics to show you it running in dynamics. I apologize for that not happening, but at this point, this is pretty much everything you would be concerned with maybe doing to either get a more detailed design or transition it to fluid flow and dynamics. And for sake of time, we're going to call that here because we do need to move on to model writing still. So if there's any questions on any of this, I'll be happy to take them after we get through with the model writing concept. Okay, so for the last topic that we're going to talk about, it's going to be how you go about creating or editing custom models. Right, so specifically when we're talking about this, we're talking mostly about equipment models or submodels, sets of calculations that are used in larger equipment models, right? So just to do a quick recap on the model library stuff, this area here is the model library manager. Every one of these tabs is a model library, and every one of these icons is a model. But specifically for model writing, what we're referring to here is the model editor window, which is used in equipment models, meaning models you put on the canvas and you connect to other models, and submodels, meaning these down here that are used to contain certain sets of calculations for specific purposes, but they themselves are not used directly on the canvas. You don't just drag and drop these on the canvas, right? So these are the two types of models that we're referring to when we talk about model writing role. Now, model writing role is very flexible and does not require any coding knowledge whatsoever. So as long as you know how to write equations like in Excel, you should be able to use this to be able to create your own custom models within the software. On top of that, this is the same infrastructure that we use for our models that come with the software. So there's nothing unique about anything that we're doing that you can't make use of on your own. You just need to understand this window and how the structure works for how to perform the various model writing related, tasks, right? So in this, well, first, let me say you need to be in model writing role. So if you are going to do any model writing, you need to be in model writing role, right? So just be aware of that. If you need help on any model writing topics, you can go to the help menu. There's a whole section on writing models that you can reference that will tell you about a lot of the things I'm going to talk about here and more in relation to editing and writing your own models. All right, so we're going to skip down and I'm going to work through a demo and I'm going to talk about sort of the general workflow that we would follow in order to create a model from scratch. And we're going to basically recreate a model from one of our training exercises and talk about it as we go through the different steps. Okay, so I'm going to open up that file. Just give me 1 second. Okay, so in this file, we have a simple heat exchanger model that we've created that has a very basic duty equation that we've applied, as well as a straightforward pressure drop calculation, right? And so if we look at this model, we can see some of the variables that we've created for this, and the equations are, being done in the background. You can see some of those equations here. Right, here are the equations, right? And it's pretty straightforward model, right? We're going to use this as an example of showing how to create a model from scratch all the way through to basically a final, product that you can use in the simulation. As I talk about these different steps, the thing that I want you to keep in mind is that you may be starting from scratch, or you may be starting from an existing model. The philosophy here is still going to be the same. You just might be starting at a different point in these steps that I'm going to go through. All right. So if you're using an existing model and all you're looking to do is modify an equation or add a new equation, you're going to be a little bit more ahead in this process than what we're going to be doing starting from scratch. But the idea of how you approach modeling is going to be the same. Right? So let's start by, if you're going to create a new model or edit an existing model, you should always do that in your simulation model library or in a custom model library. Right, so either create a new library that you can keep all your customizations in if you want all of your files to be able to have access to it, or if it is for just a specific file, do it in the simulations model library. So we're going to create a new model. All right, we can right click, choose create new model. And when we open up this model, I'll close this and I'll leave this open. First thing we're going to want to do is give it a name for the model. So this is going to be my demo heat exchanger. We can even give it some kind of naming convention, so that way when it's placed on the canvas, it has a certain naming convention associated with it. So we're going to call this maybe demo heat exchanger and start with a value of 1. All right, and then I said this the other day, if you have a description field, you really should put in something for the description, because that's going to be utilized elsewhere in the software for people to understand what they're looking at, right? And so I want to provide a meaningful description here so that the pop-up tells my users how to use this model, what it is. Right, so if I type that in and I hover over here, you can see my message pops up. Right, and so this is useful for being able to educate whoever might end up using your model on how to use it or what the model is. If you look at some of these other models in the Canvas or in the other model libraries, they all have descriptions that say what it is and or how it gets used. Right, so these are all because someone wrote something in the description field. So it's a good idea for you to write a description. And then you have a couple of other options here in the general tab that are worth considering. We talked about the concept of roles, right? If you're a model writing role, you see more, you can be able to edit stuff. If you're in simulation building role, you can't edit, but you can, it streamlines your view so that way you're only seeing what's most important, right? If you want this to be hidden based on the role, then you check this box, right? Checking this would make it so that a user can't see it when they're in simulation building, but they would see it in model writing, right? Do you want to be able to use this as a connection model? So we talked about that the other day. You have these connection models that can be embedded on a connection. If you want the user to be able to select it, like this list here, this checkbox has to be checked. If you want it to be a replaceable submodel, meaning something you can select as a pull down for one of the various submodel selections, right? The easiest example of this that I could think of would be the reactor, right? If we have a reactor, we click on here, we're picking a reaction submodel, right? There's a certain reaction submodel that we're picking, right? That selection is only there because this box is checked, right? So that's what it means to use it as a replaceable submodel, right? So you want to consider those And then you're going to want to go from here and you're going to want to go down to icons as the next step. Now, even though there's, a bunch of different categories here, it doesn't mean we go top down all the time. There's a reason why we go from one to another. And so you're going to want to follow the recommendations I'm talking about here. And you'll see why as we go through and we build out this example. Okay, so I'm going to come down to icons, and I can change the way that this icon looks by selecting a different icon file. So if I click this button here, it opens up a folder where I can browse for various XAML files. These different file formats all have the icons for the various models within our software. And so you can browse and you can pick one that suits the type of model that you're going to be doing. In this case, we're going to do a heat exchanger. Now, if you had a software program that could create XAML files, and there are programs out there that do this, you could theoretically create your own icon, right? So you can create an icon for your custom model that fits whatever you want it to look like, instead of one of our icons that we already have established in there. Right, so now I've chosen an icon. The next thing I want to do is I want to go to ports. This is where we're going to define our connectivity. So how does it connect from one model to another? The fact that we have this outlet port here, or that we could connect this stream from the source into the heat exchanger, right? Those are all defined by ports. These are different connections. So we click this little plus sign to add a new port. And when we're in here, we need to define what kind of port it is, how many connections it can have, and if it's inlet or an outlet port, right? So we're going to start by choosing the direction. This is going to be our feed port, so it's going to be an inlet port, right? If it was a product, it would be out. And we're going to choose how many connections can connect to it. If it's a single, then only one connection can connect to that one port at a time. If it's multiple, it's going to look like a bar. This is what our headers look like, right? And you attach to a header, or for the inlet or the products, you can have as many things attached to this bar as you want. And that's because it has a multiple connector. Now we're going to go with a single. And then the next thing we're going to want to do is select the type of port that it is. So the other day we talked about connection models, and I said that connection models have they take this minimum information, right? This is the minimum information shown right here. They take this information and then they calculate other properties that we want to see using this information, right? So the stream model in the process model library is a connection model that takes this and calculates mass flow rate, volumetric flow rate, temperature, so forth, right? This is the minimum information, though, that's being supplied. Right, and that's coming from the port type, whatever we select here, right? So when we select flow port, that's what this selection is here, this window, we are telling it that we want it to transfer this information. Right now, the other thing that we're doing by selecting this is we're telling it what it can connect to, right? If I want my model to be able to connect to other models in the process model library, I need to select flow port to be able to connect flow-to-flow connections, right? So if I'm trying to make this custom model and I picked something else, let's say I picked flare port, which happens to be the default for flare model library models, I would not be able to connect my model to my models in my process model library. I need to have the same port type in order to connect from one connection point to another, right? So flow port is going to be the one you're going to use most of the time, but it also all depends on the type of connection that you're looking to make, right? If I want to make a controls connection, meaning I'm connecting it to a PID controller, then I need to set this as a control port. If I'm trying to do a mechanical connection, like I want to connect it to the motor model, right? We have a motor model over here. Show it real quick. Right, here's a motor, right? If I want to connect it to that, I'm going to need the mechanical connection. right? I have a model over here called an HXC model. It's a heat exchanger model that's designed to be connected to a drum to transfer the duty of the heat exchanger to the drum, or vice versa, right? That uses a heat port connection, right, to make that connectivity between the HXC and the drum, right? So every one of these is going to be a different way of connecting to other models. You can only connect to the other models that share the same type of port, and whichever you select here is going to dictate what property information is transferred from model to model. Now, the flow port model, the flow port connection type, is the most common one that's used in the process model library, the steam model library, the cooling water library, even other model libraries that are more advanced, like membrane model library, the renewables model library for the electrolyzer. They all use that flow port because that's the most common and most base level amount of information that's required to transfer from one model to another to solve the equilibrium calculations. Right. And so when you think about what is being provided here, it's information that's going to help you solve your thermocalcs, right? This is the base level information that solves most thermal calculations, right? So that's why you see this port being used everywhere and this information in that flow port. All right. We're going to come back to talking about this information itself when we move on to the next stage of the model development. All right, but for now, the next thing we want to do is make sure we name this port. We don't want to name it port 1 because if we leave it as port 1, every time we write an equation that reference to the feed coming in, we're going to have to use the name port 1. So we want to give it something that's a little bit more meaningful that we're going to remember. We might want to give it feed, right? So know that it's the feed port. We might want to say in or inlet to know it's the inlet port, right? But whatever we choose here, this is the naming convention we need to use elsewhere in our equations and other things that we do to set up the model. All right, so now I can see I have my port here on the icon, and I can click and drag this to where I want it to be on my icon. And once I have this port in place, the very first thing you're going to want to do is take a source, put it on the canvas, and then take your model and put it on the canvas. Connect these together. One of the key features of model writing within Aviva Process Simulation is that you can actually use the model while you're doing the model writing. And this is important because as you develop the model while using it, you can use all of the different feedback you get from the simulation file to help you build the model. So things like the solution badges up here, right? The information that's over here in the simulation manager, all this information is going to help us determine what we need to do with our model writing. All right, and so when I go forward from here, I'm constantly going to be looking at this information and this information to help me determine what I need to do in order to set up this model, or what else I still need to do that I haven't thought of, right? So right now I'm satisfied with the way that I have this set up. I'm going to want to go to the models section next. And the whole reason why we want to go to the model section is because this is where we're going to pull in any submodels that we want to use. Now, the reason when we do this now is because every submodel that we pull in is a set of calculations that we don't have to redefine within our model, right? So if I pull in submodels to do our thermodynamic calculations, or in this case, I have a heat exchanger, maybe the LMTD calculations, right? Those are less equations I need to write in my equation section, less variables I need to define, right? Because the submodels themselves are going to have them. I'm just pulling them into my model to utilize them, right? So what I might want to do here when I create or when I go to the models is create what's called a state submodel. Right, this is going to help us perform the thermal calculations and sort of define what's like inside of the heat exchanger model itself, right? So when we're thinking about our model's design, there's an easy way to sort of think about data flow through the model, right? You have what's coming in. Once it's in the model, you have what's happening in the model. And then you have everything that's coming out of the model. So there's an in, there's a state effectively, like what is happening within the model, and then there's an out, right? We already have the in. That's this port, right? And we're going to eventually add an out. So that's going to be our product, right? But what's happening internally within the model, that's going to be dictated by things like our state submodel and the equations and variables and stuff that we add within this model. Right? So at this point, I want to create a state submodel. So I can go state. We're going to call it state. And I'm going to go and I'm going to try to connect this to a specific state submodel to use for the thermal calculations. Now, the way that I want to do this is I wanted to use the state calculations that equate to whatever the fluid is that's coming into the file. All right, so I could go to submodels. In the very top of the submodels library, I see there's several different state submodels that I can utilize. All right, and while compositional would be the most versatile and would probably work just fine for me in this case, if I choose compositional and then I have a fluid later that I feed it that's an incompressible liquid, it's going to fail to solve because the compositional state submodel is not set up to handle incompressible liquid fluids. It's only set up to handle compositional fluids, right? So there's a better way of setting this up that we need to do, and which isn't ready yet from these selections. So what I need to do is I need to come up to parameters, and I need to create a fluid type parameter. This is what's going to store the fluid definition from my feed. Right, so I can see I've set this up now, right, and it doesn't have a value yet because we're going to get the value from the feed coming in, and we have yet to set that up. We're going to do that next. All right, but now that I actually have this in place, just the fact that I have this fluid type parameter in place, when I come here, you can see I have two new options available to me. One of them is the fluid type state model. So my state submodel within my heat exchanger is going to use whatever the fluid's state submodel is. Now, if I go to a fluid, so here's my fluid, there's an area called models here. And you can see there's a state submodel in the fluid's definition. Every fluid has this, right? And by default, whatever is set here is going to be connected to the selection here for thermotype, right? So if this fluid was set to a different fluid type, thermotype, this down here would say submodels and then that thermotype's state submodel, right? So the fluid now sets the the state submodel type, and the model just uses whatever the fluid uses. All right, so this is a more robust way of setting this. Okay, so now I have my state submodel set up. When I come over here and I look, I can see, oh, look, there's the state submodel. And if I expand it, oh, there's nothing here yet. Now, this, in my opinion, is a defect, which I'm taking up with development to talk about them about, but this isn't going to populate with anything until we transfer something to the state submodel from the inlet coming in. All right, so we're going to see that happen in just a second because that's the next part that we're going to do. All right, so now we have the state submodel set up. Now we want to start defining some connections. Connections are one-to-one relationships within the model, right? So we commonly use these wherever we have equations where it's this value equals this value, right? This variable equals this variable. That's a one-to-one relationship, but that's a variable connection. You can also have connections that are parameter connections, that are port connections. There's different types of connections that we can make. And this is going to do everything from establishing certain equation relationships to transferring data from one part to another part within the model, changing connectivity within the model. There's all kinds of things that we can do with these connections that we're going to define. Right, so we're going to define a connection now. It's going to be a parameter connection, so we're going to leave it like this, and we're going to transfer the inlet fluid type. All right, so what fluid is the feed using? And we're going to transfer it to here, to the fluid type. All right, so I just type fluid type. I don't have to type in or state right now because I'm referring to the parameter within the model itself. All right, so I just type fluid type. Now, when I come over here, I can see my fluid type parameter is populated with the fluid, right? The depth fluid, right? That's coming from the inlet. All right, so I can see I was missing something here, and now it's populated something over. We're going to do the same thing for the state submodel. We're going to do in fluid type state dot, and I'm surprised it's not popping up with options here. We're at type state dot fluid type. So I hit enter. Now it's satisfied. Nothing's populating yet here. Let me close and reopen this. Sometimes this happens. You get a little bit of a hiccup in the connectivity of the software. But things are looking better now, despite the unsquare and unsolved state. This is actually what we wanted. So now we added a new connection here to transfer the fluid that's coming in, just what fluid am I using, to the state submodel. And when we look over here and we look at our heat exchanger, we expand the state submodel, we can see, oh, there's a lot of red. What's going on here, right? Why is it all this red? Okay, so as I said at the beginning, when we put this on the canvas and we connect it, we can use this feedback to get valuable information as far as what we still need to do within the setup of our model. Unlike a normal simulation, this being red, right, and these things being red, is not designed to tell me, oh, come over here and check some boxes, right? This is not what I'm supposed to do. Right? So I checked 5 boxes, which is how much I needed, and now it came back and it says it's square, right? That's not what I was supposed to do. What I'm supposed to do with this feedback is say, oh, the state submodel still needs information in order to solve, right? I haven't transferred enough from the feed to the state submodel so that the state submodel has all of the information it needs in order to solve properly. So now I can create some connections. We're going to do variable connections, and we're going to transfer some data from the feed to the state. So now we transfer the pressure over, and now we're down to 4. It's for another. Now we transferred over the composition information. So now we're down to 1. Now we transferred over some enthalpy data. Now we're square and we're solved, right? So we let the program tell us what we still needed to do within our model, right? It wasn't, there was no second guessing, there was no questioning, oh, I don't know what I need to do. It was the program told me this, and I added what it needed in order to get it to solve. And you may ask yourself, how did I know that these were the conditions that it needed, right? I knew that because I know how the state submodel is designed to work. It's designed to do the thermal calculations, which this is the standard basis for most thermal calculations. It's why this information is populated in the port, right? Pressure, enthalpy, composition, right? I couldn't provide any other information because it's not here in the inlet, right? And it wouldn't have sufficed for the state submodel, right? So having some knowledge of what the model is that I pulled in here and what it requires to solve helped me understand that these are the properties I needed to supply to it. But I let the program tell me I still needed another condition. I still needed another condition. I still needed to provide something else, right? And that's what helped me know that I needed to add these things in, right? When you are doing your own modeling, you're going to follow this process, this thing that I just did with the state submodel for every submodel you pull in. So right now, my state submodel is satisfied, right? And I could say right now that I'm good to move on with whatever I plan on doing next with my custom modeling. However, if I wanted to add another submodel, right, I would be going through this process again. And not only would I be going through this process again, I would have to look back with everything that I do and check back against the things that I've already done, right? So the things that I've already done here may be affected by the new things that I'm adding in moving forward. And that's what we're going to see on this next part. I'm not going to add any more submodels, but what I am going to add is my first equation, right? So my first equation that I'm going to add is for my pressure drop. Right, so I'm going to add in an equation here, and I'm going to say my inlet pressure minus my pressure drop equals my outlet pressure, right? When I click enter, first thing that's going to happen is it's going to tell me it doesn't know what dp and out.p are, right? Because one, I haven't defined those and they don't exist anywhere yet, right? So I'm going to have to go back now, right? I'm stepping back yet again, right? I need to now have an outlet. So I'm going to create an outlet stream. Right? And I'm going to put it over here. And I'm going to need to create, well, I'm not going to create it yet. I will leave it at this for now. Let me delete this. Right? And I need to create a DP variable. So I'm still missing a DP variable, right? So I'll come up here, create new variable, tell it what kind of variable I have. Pressure drop, call it DP. This comes in some default values and default min and max ranges and some other settings over here. The unit of measure that's shown here is the internal units of measure that Viva Process Simulation is going to use. When I write my equations down here, I do need to make sure that I use the internal units of measure. If I need to use different units of measure, I need to bake in to the equations that I write the conversions, right? So if I knew that this needed to be in a specific unit of measure, I would do something like this, whatever the conversion happens to be, to convert it over to that unit of measure, right? So you have to build that into your formula to adhere to the internal units that the software is using. All right, so now I have my pressure drop defined, and it tells me that I'm satisfied with this equation, but I'm unsquare and I'm unsolved, and I don't exactly know why. So I need to go and look, right? So I come over here, the heat exchanger tells me, oh, I need to add a spec. Now, when I add a spec here, I'm not trying to do it here in the simulation, right? What I'm trying to do here is have this tell me I need a spec and then use the default spec status of my variables to help re-square the simulation. So in process mode, that's this column here, I want DP to be specified by default, right? That's how I know to check this box, right? So now I have the pressure drop implemented. If I look at this, you can see it's specified by default. Let's check and make sure that everything is working correctly, right? So I have a feed pressure coming in. It's 101.325 kPa. I have a pressure drop of 50 kPa. My outlet shows 51.32 kPa. Great. My pressure drop is working correctly. I'm done. Or am I? Let's check the state. The state still shows that the pressure within there is 101.325. It didn't apply the pressure drop. And the reason why it didn't apply the pressure drop is because we are defining the pressure in the state to be equal to the inlet pressure right now, right? So this is not correct anymore. Even though we put that in to begin with to satisfy the state submodel originally, we are now imposing a new change, a pressure drop, that we need to adjust what we've previously done in order to account for that properly. So in reality, it's not in dot P equals state P, it's out dot P equals state P, because we want the pressure drop to be applied to the state pressure. And so now we see this, we can see it's updated it accordingly. Right? Now, we added that outlet stream, and we have properties here that aren't populated. And so one of the things that we can use is, even though we're square and solve, the fact that these are grayed out means they don't belong to anything. Nothing is populating them. Nothing's calculating them. We still know that we need to provide these pieces of information. And so what we can do is we can start adding in the information that's missing here. Right? So we need to transfer the fluid type. Right? So we can do the same thing again. Right? So that transfers that over. We need to transfer the flow rate. We can do in F equals out F because there's no mixing or splitting of flow, so it's going to be the same flow rate, right? We could, if we wanted to, and we're going to change this later, how we delete this, right? We could say something like state.h equals out.h, right? Or state.h equals out.h, right? There's a couple things that we could do, but we're going to delete this because this is not actually going to be used in the end, right? But the idea here is that this has yet to be populated. We need to do something to account for that, right? So the next thing that we're going to do is actually going to fix that. Oh, the other thing we need to do is transfer the composition. So we should do that now while we're at it. This is the same thing as the molar flow rate. It's not going to change, so we'll just set in equal out. So we took care of that. All right, so we're going to add another equation here. All right, and the next equation is going to be our simple duty equation that we want to implement. So we're just going to expand the existing heater so we can see the equation. We're going to type it out. Duty equals in dot F times out dot H minus in dot H. Enter. When we do this, it tells us it's missing duty. Okay, so we need to go and add another variable. We're going to call this duty. Now that we've added that, we're satisfied. And it shows us we need to add in another spec. So just like before, instead of adding it here, we're going to want to add it here. All right, so we're back to being good here. All right, and now let's look and check our results. Make sure everything's working out reasonably. So right now we have no duty. So we don't expect anything to really change, right? Everything should be the same. So the enthalpy coming in equals the enthalpy in the state equals the enthalpy coming out, right? If we apply a duty, we should expect to see some kind of change. Okay, so we added 10 kilojoules per second. This is our in, this is our out. it clearly changed, right? But our state did not change. And that's again because of this, right? We had a relationship before that equated the inlet to the state. So we need to adjust this yet again so that it actually takes the duty into account within the state submodel, right? The other thing that we might want to do, and actually I'm going to go back because this is another way that you could tell that something is wrong. All right, I'm going to go back to the way it was defined before. We're going to do one more thing here. When you look at the stream port type, right, there's no temperature, right? Temperature is typically calculated in the state submodel using the enthalpy value that's calculated, right? And so for me to get the temperature, I would have to refer to my state submodel to see what my temperature value is. One common thing to do with the way that you write your models is to pull a variable from a submodel up to the main model. So I might want to put in temperature here, and then set it up so that I'm transferring the state temperature up to the main model, so that way I can see it up here on the canvas. Right now, when it's up here on the canvas, one of the things that I might notice is that as I changed my duty, my temperature didn't change, right? So that's another dead giveaway that I had a problem with the way that the duty is set up, right? And that's when you come and you realize, oh, this needs to be changed to this. Right now, when I apply a duty, I see a temperature change, right? And that's more reasonable. That's more like what we expected to see out of it. Okay. We are, ironically, we're done, and we're done pretty much on time. There's a lot more that can be discussed when it comes to model writing, a lot of capabilities that we didn't even get to get into or touch on. I would consider them extra, not necessarily required, but definitely useful depending on the different features, such as conditions, right? That's always stuff that you can reference the help documentation for more information on. But what I wanted to get across here, and hopefully I did that, is that when you're doing model writing, it's good to place the model on the canvas and use this feedback from the solution status, from the simulation manager to help guide you on what you need to do with the model writing, right? To help tell you need to add more things in, you need to change certain things, you need to check certain check boxes, right? Those little things, you get that feedback from seeing it being used while you're building it. So hopefully that was made clear through this demo. All right, with that said, let's open it up for Q&A, and that's it for the sessions. If there's any other questions as well, you don't just have to ask questions on today's topics. If you guys have any questions on anything related to APS, feel free to ask them now.
We have no questions in the chat today, but let's see if someone types some question now. Okay, I think it's that. Thank you everyone for joining us. Thank you, Richard, for those days and so much knowledge shared. So we will make those videos available for everyone. Just let me know if you didn't listen or didn't receive an email from me, okay? Oh, I think there is someone type. Oh, no, okay. So thank you. Bye-bye.
All right. Thank you, everyone. Take care.